Yep. Okay, so the way we prevent ourselves from making too much heat, overloading an X-ray tube, damaging the filament, damaging the anode, is by referring to these charts that we get with our equipment, okay? Charts like the radiographic rating chart, anode cooling charts, and tube housing cooling charts. So the first thing we'll need to do is we need to be able to calculate, in principle, how much heat we're making during an exposure, okay? So there's a unit called the heat unit. The heat unit. So this is we're going to have a formula for the heat unit. The capacity of an anode or tube housing to withstand heat is measured in heat units. So it'll say this X-ray tube has a maximum capacity of this much heat given in these units called heat units. One heat unit is defined as the product of the kilovoltage setting, the milliamperage setting, and the time setting. It's all multiplied together. kVp times MA times the time setting. We'll give an example in a moment. This is for your standard single-phase X-ray machines. So single-phase AC rectified current. Machines that use multiple phases, multiple staggered pulses of electricity, they produce more heat because you're using more electricity. Okay, so in order to do the formula for those, you have to add in a little conversion factor of 1.4 because multi-phase, high-frequency units, because they generate more heat, we have to add in that. So they generate about 1.4 times the heat, about 140% the heat that a less efficient system would. They generate more heat, but also remember they do it. They generate more heat, but they generate more X-rays more efficiently too. So you can make shorter exposure times in the long run. So it does kind of even out. So let's give an example here. I'll come back to that if you guys need me to, but I think you'll be able to get it as we do our example. So this question's a practice question. It says how many heat units are generated by a high-frequency X-ray machine, assuming the exposure was done at 80 kilovolts, milliamperage was set to 300, and time was 0.1 seconds, a tenth of a second. By the way, how much mass is that? What's the mass number? 300. If it was for 1 second, it would be 300. Mass, not MA. Remember, so I will do this in Principles of Exposure. We'll like explicitly do a bunch of mass calculations, but some of you should know this. Milliamperage times time is mass, MAS, milliampere seconds. Okay, milliamperage is a number telling you how many free electrons are going across the gap, right? So it's going to tell you how many electrons you have to make X-rays from. More milliamperage equals more electrons equals more X-rays produced. Time is just telling you how long your exposure lasts for, okay? An exposure of 1 second versus an exposure of 2 seconds. The 2-second exposure would give, all things being equal, the 2-second exposure would give twice as many X-rays, produce twice as many X-rays. So if we want to know the total quantity of X-rays made during an exposure, we take milliamperage and multiply it by time, MAS, milliampere seconds. 300 times 0.1 is 30, so it'd be 30 mass, okay? You know that because if you shifted the decimal point over one place, it would be 300 times 1, which is 300. So shift the decimal point back to the 0.1 position, and the number gets 10 times smaller. 300 divided by 10 is 30. So 30 mass. You don't have to do mental math, right? You can plug it into your phone. So you're always given a calculator. No one's going to make you do mental math. But you should work on it. Anyways, all that being said, the mass number you could just have, and you could just say what's the mass times the kV, okay? Or you can write it all out separately. kVp, MA, and time all separately with the added 1.4 because it's a high frequency machine. Anyways, 1.4 times 80 times 300 times 0.1 happens to be, hopefully, I didn't double check their math, I'm trusting it, 3,360, okay? So in that exposure, with that much voltage, that much amperage, and for that long of an exposure, we've got 3,360 heat units produced. So now we could go to a chart and say how many heat units were produced, and we could ask how long does it take to cool from that amount of heat produced. And if we made that much heat, could we make another exposure without exceeding the capacity of the equipment? Okay. It's not, but if your capacity was 4,000 heat units and you made this exposure and then immediately you wanted to go make another exposure of the same level, right, you wouldn't be able to. If you doubled the heat units from 3,360 to 6,720, which is what I think double that would be, you would exceed the heat capacity for a 4,000 heat unit machine. Okay, so heat units are a way to calculate how much heat you produce during an exposure. As well, you'll have to know, you'll have to be able to set, and what's really nice is the circuitry pretty much does this for you, but you can ask, for a given kilovoltage, a given MA, what's my maximum exposure time my system can manage, okay? Or, for a given MA and exposure time, what's the maximum kilovoltage? So there's three things on this graph. The vertical axis, so we'll do a little bit with this. The vertical axis shows kilovoltage. The horizontal axis shows time, and these plotted lines show the MA numbers, okay? So I could ask, dangerous. So I could ask for, a 0.1 second exposure at 500 MA, what's my maximum kilovoltage, okay? So I go to 0.1 seconds, 500 MA, my maximum kilovoltage is 60. Okay. I could also ask, given my kilovoltage and my MA, what's my maximum exposure time? Okay. So let's say we want to go to 80 kilovolts and 300 MA. Okay. 80 kilovolts, like the last question we did. 80 kilovolts to 300 MA. What's the maximum time our system can use without overloading it? So go to 80 kilovolts, move horizontally until you run into the 300 MA arc. Okay. And then the line you ran into, follow that down, and you're at 0.2. Your maximum exposure time is 0.2 seconds. So your maximum mass is 300 times 0.2. So it's 60. Okay, 60 mass is your maximum MAS setting when you're at 80 kVp. Okay, so and every machine's going to have one of these. In principle, it's in the manual. Okay, yeah, go ahead.
So then that relates to the heat unit, because then they say this is the maximum.
Yeah, behind the scenes there's a heat unit number being created here.
Right.
And this is not showing you that number, this is using that number to tell us what our maximums are.
But like you said, our machine is 4,000, and then so the heat unit produced was 3,300.
Right.
So we can't go beyond that number because then you would jump over the 4,000.
Exceed the capacity, okay. Yeah.
So that's us.
So this chart here, exposure rating charts, just tells you, given whatever two settings you want to make, what's the maximum number for the third setting, okay? We have three settings, right? KVP, MA, and time. Given two of them, what's the max thing we need for the third one, okay? So I can say for 140 kV and 2 seconds, can I make an exposure at any MA setting at 140 kV in 2 seconds? Well, 140 kV, go all the way over to the 2 second line. There is nothing to run into over here. Okay, I don't touch any of these MA lines, so I can't make an exposure at 140 kV for 2 seconds. Okay, I can only make exposures that interact with these MA lines. Okay, so given two things, what's the third one? That's the point of this. All right, let's take a look at the next thing. The next type of chart that's useful are cooling charts. So these cooling charts show you on the vertical axis, at the top of the vertical axis, the maximum capacity in heat units. The x-axis, horizontal axis, shows you time since those heat units have been created, and so you can ask, given an elapsed amount of time, how much will my machine have cooled to? Okay, so if we start 0 time, we heated our machine up to 350,000 heat units. Okay, we start at 0, time equals 0, we're at 350,000 heat units. We have reached our maximum capacity for the equipment. We need some time to let it cool down before we can make our next exposure. Okay, so if you were making, let's say, less than 50,000 heat units, then you would want your machine to cool down to, at least 300,000 heat units before you make your next exposure, right? Your capacity is 350,000, and the next exposure you want to make is something less than 50,000. So let your machine cool down to about 300,000 heat units before you make your next exposure. Well, how long does it take to get to 300,000 heat units? That's not very good. Let's try to minimize that a little bit. Good. So you say I'm at 350,000 heat units, and I want to know what time is it going to be when I'm cooled down to 300,000, right? The first vertical bar over, which would correspond to 1 minute's time, if I follow this line down to 300, this line intersects the 300 horizontal line before we get to 2 minutes, okay? So I can't give an accurate number on how long it's going to take. What I can say really easily, before 1 minute. What I can say easily is if we start at 350,000 heat units and I want to wait till we get down to 300,000 before I make my next exposure, I got to wait some time, about a little less than a minute, okay? So let's say we waited 10 minutes, okay? How cool would the machine be, okay? So we follow this line over and down until we run into the number 10 line. So 2, 4, 6, 8, 10 here. 10 minutes runs into this plotted line somewhere between 0 and 50. It's not a very accurate graph, right? So we know at 10 minutes time, we are below, this plotted line is below 50,000 heat units. So wait 10 minutes and you are less than 50,000 heat units in your machine still. Okay, your machine has cooled down a lot. How long does it take the machine to cool down to 0? 14 minutes, and this plotted line showing the heat runs to 0.
So this graph shows you the cooling rate of what, both the anode and the...
This is the whole tube, just
whole
as
tube.
the average heat of the entire tube. That's a really good question, because everything heats up maybe a little differently, right? This is just saying what's the average heat of the whole system.
Okay.
Yeah. So given you have maxed out your machine, it's going to take you 14 minutes with this machine for it to cool down to 0, and now you're cool again. When you're cooled to 0 heat units, you have no heat left over in your machine's cold again, okay? It may need to be warmed up. So, if you wait 2 or 3 hours, so this happens a lot, right? You take an x-ray, maybe you warm your machine up in the morning. You warm up your machines in the morning so that you don't damage them. You build heat in the equipment so that when you make your exposures, you're not making exposures on a cold machine. You guys know it's like not a good idea to take your car on a cold morning and start it up and start doing burnouts in your driveway, right? It's bad for your car's engine to run at high energies when it's cold, okay? It damages things, it warps things, it's bad for the engine, okay? Same thing with our x-ray machines. It is bad for them when we run them when they're cold. So we turn them on, we let them idle for about 15 minutes. We turn them on, just kind of let them be for about 15 minutes. There's a tiny amount of current just when the machine's on running through the filament. Not really useful current, just a small amount, but that turns into heat, slowly heating up the equipment. So you come in the morning, 15 minutes, you let your equipment just be on, and then you come back and you make warm-up exposures to slowly build heat units in your machine. But then, it's 8 o'clock in the morning, your machine's on, you got it all warmed up, and then you don't get a patient until, 10 o'clock who needs an x-ray, okay? Your x-ray machine's been sitting for 2 hours. Well, if it's this one, it only took it 14 minutes to cool down to 0, okay? It's cold by the time you get to 2 hours, so what should you do before you x-ray that first patient? Warm it back up again, right? Which means that it's probably not a super important idea to warm it up until you're sure you're gonna have some patients coming soon, right? No point in warming up a machine if you know you're not getting patients for hours ahead of time. Okay, there's no point in it. Anyways, that's all to say we can, in principle, calculate how much heat we've made during exposures. You can calculate the amount of heat you make during warm-up exposures and see how hot you warm the tube up to. And given some amount of heat produced, you can ask how long does it take to cool down to 0. Okay? Anyways, that's the point of these cooling charts.
So you said a key word, you said when you max out your machine. So, so just on this graph, 350 would be, on the machine that we use over at the site that I'm at, it'll tell you right there how much of a percentage it'll go up, as far as like how hot the machine is.
Really?
It takes a couple minutes, literally, like say if we're doing torso, lumbar, or thoracic spine, it's going to get a lot hotter than if it would if it was doing a hand or a foot x-ray. So there's a little percentage on the machine.